Okay, finally, the last chi-square test is for homogeneity. So think of that as like sameness. The question will often say something about different or sameness or something like that. Um, I like this too. We compare a single categorical variable with multiple populations for treatment. So oftentimes there's like three or four different samples of stuff. It's not one sample. It's you're comparing it to multiple different populations. So just subtly different than the independence test. Does background music influence what customers buy? So they're saying compare three randomly assigned treatments, and so there's treatments on this one. That's different than what we've seen, not just random samples. No music, French music or Italian music. Uh, they said, did you order French, Italian, or other? If you listen to French music, do you order French food? So here's the data. It's hard to tell too much from that. Um, so the hypothesis, there's no difference. It's the dull null hypothesis. There's no difference. Playing music is not going to influence what you order for food. It's just not going to happen. Well, the alternate is there is a difference. Maybe if you play French music, you might be more likely to order French food. So we're not saying all the distributions are different. We're just saying there is a difference. There's at least one difference there. Same three conditions. You'll see it applied a little bit differently here because of the way this test is set up, especially with the less than 10% condition. Those are still the same. That's still the same. Nothing's changed. Still, number of rows -1 times number of columns -1 for degrees of freedom. Okay, so let's look at an example. Pew Research conducts a survey about a variety of topics in many countries. One such survey investigates how residents of different countries feel about the importance of speaking the national language. Independent random samples, there were more than one, that indicates this might be chi-squared homogeneity. The United Kingdom, Australia, and United States. How important do you think it is to speak English? We're the same variable, speak English, applied to three different situations, three different countries, in fact. So there's the two-way data. Do these data provide convincing evidence that speaking English differ for residents of Australia, United Kingdom, and United States? So differ, there again, that word differ or different. So this is definitely a test for homogeneity. The procedure is largely the same as independence here. The null is nothing's going on. There's no difference. You start that way. There's no difference in the population distributions of opinion by speaking English for all three of those countries. The alternate, there is a difference. So independent random samples in the three countries. No, use the plural there because they were separate samples. This is where you have to test each sample separately. So I think they asked 1,000 people in Australia, 1,460 in UK, and 11,000 in the United States. All expected counts. So we do the test again the same way. So to get the expected counts, you want to set up your matrix. This would be a 4 by 3, I believe. So 4, tab, 3, tab, enter. I type in the numbers. I did something wrong. Okay, let's see, where did I get off? Okay, so I messed up right here. Okay, so 40. Oh, I put too many numbers. I might have put some of the other numbers in there. I don't always pay attention to what I'm doing here when I'm typing. See if that looks right. Okay, I think that looks good. So we're going to store that. So Control R, English. Do the test, menu 6-7, type a two-way table, two-way test for chi-squared. It's called English. There it is. And if you want to expect matrix, hit var stat expect matrix. Those are all the expected counts. So now we have the p-value. The degrees of freedom is 6 because it's 4 minus 1 is 3, times 3 minus 1 is 2, 3 times 2 is 6. Chi-squared is 59. Oh my goodness. So p-value is extremely small. It's a scientific notation number. It's like 0.000006. Sometimes we just say the p-value is approximately 0. It's okay to say that. I'll see what they say when they do it. But we get all those values. And so all expected counts at least 5. You have to write those down in your paper somewhere. You can put it as a table, as a list, whatever you want. Really like to see this. Do the first couple, maybe the last one. Huge p-value, huge chi-squared value, very small p-value. Again, draw your graph if you want to, but it's so far out there. You could use chi-squared CDF to get that if you know the chi-squared value is 68.57. They said the p-value, sometimes they'll write it this way. Right. So sometimes they'll say p-value is approximately 0. That would be perfectly fine to write. They wrote less than 0.0005. They were like so many decimals. So because the p-value is so small, it was approximately 0, which is less than alpha. We reject the null. There is convincing evidence of a difference in the opinion about speaking English for the different countries. If you want to know how the distributions differ, you have to do a follow-up analysis. So this just tells you they're different. So it doesn't, going back to the Malcolm Gladwell, these kinds of tests don't tell you which way they go. It just says, yes or no. There is a difference. That's what it tells us. You must write down all the expected values, right? You can get it from your calculator, no problem, right? 2 researchers asked 150 volunteers to recall the details of a car accident they watched on video. 50 of the volunteers were randomly assigned to respond to each question. About how fast were the cars going when they smashed into each other? Another 50, same question, but the word smashed into was word hit. They did not ask the 50 volunteers to estimate the speed at all. A week later, the researchers asked 150 volunteers if they saw any broken glass at the accident. There wasn't any. The two-way table summarizes each group's response to the broken glass question. What a strange thing this is. Okay, so which chi-square test should be used to analyze these data? Explain your reasoning. Whew. So you're wording the question differently. There is only one sample, but there are 3 assignments there. Is the response going to be different? My thought is probably homogeneity. Yeah. So that's what it says there. So only one set of totals was free to vary. So there is no difference in the responses. So the true proportion of people, like the ones in the study said they were broken glass, are the same for all three treatments. So there's no difference. There is a difference. They're not the same. The p-value for this test is 0.02. It says, what conclusion can you make at the 1% level? Because the p-value is greater than alpha, we fail to reject. There is not convincing evidence that people who say there's broken glass are not the same for all three treatments. Name 2 ways you could increase the power of the test. You can make the significance level greater, because that's going to make type 1 errors increase, which makes type 2 errors decrease, which makes power go up. Or you can make the sample size larger. That's always a great way to do it. That's like number 1. Okay, that's your lesson.